we have looked at CO2 emissions and greenhouse gases. Here from the IPCC 6th assessment report, I have collected certain key figures that tells us what is the impact of these greenhouse gases on our climate and why that is harmful to our future generations and to us today. Okay. So here let's look at it in a little bit more detail. So here, this plot is the amount of warming that has happened in the world today. So between 2010 and 2019 observed warming. So usually climate is a mean value, a mean decadal value. So this is the average temperature rise in the 2010 to 2019 period relative to 1850 to 1900 period. So before the global warming and associated CO2 increases rose, what was the average temperature of the world? That is taken as the average mean temperature of 1850 to 1900 period. Now, how much is the average temperature in the 2010 to 2019 period higher than the average temperature of 1850 to 1900 period? That is what this bar graph shows, and the value is around 1.1 degree centigrade. Okay. So today's global temperature is 1.1 degree centigrade higher than the 19th century global temperature. Okay. Now, what is the cause of this warming? So this second slide, these two slides basically shows that. Okay. So the total temperature change due to human influence is this 1.1 degree centigrade. Okay. This is caused by warming caused by the greenhouse gases, CO2, methane, N2O, fluorocarbons, and that total warming is actually 1.5 degree centigrade. So the actual warming caused by greenhouse gases is higher than the observed warming today. Why is that? Because there are other things human beings have done that have actually cooled the atmosphere. So other human drivers, and we will discuss this in the next slide, in the next figure, have actually cooled the climate by 1.4 degrees centigrade. So total 1.5 minus 1.4 is 1.1. Natural variabilities like solar, volcanic and internal climate variabilities have contributed nothing. So the entire warming is due to human effect alone. And here is the individual contributors to the cooling and the warming effect and their impact. The largest heating is carbon dioxide, which has led to a warming of around 0.65 degrees centigrade, followed by methane, which has led to a warming of around 0.5 degrees centigrade. Then you have actually the volatile organic compounds and carbon monoxide, which has caused a warming of around 0.2 degrees centigrade. Then you have the halogenated gases and nitrous oxide, which have caused a warming of around 0.05 or 0.1 degrees centigrade. Okay. There is also another pollutant called black carbon. Okay. So remember these ones, volatile organic compounds, carbon monoxide, black carbon, these are pollutants. So they pollute the atmosphere, but they are also having a heating or cooling effect here. So for example, black carbon is basically soot particles that have been emitted in the atmosphere, and then they kind of get deposited on ice surfaces. And so the ice surfaces become black, and they can now absorb more sunlight, because black surfaces absorb more sunlight than white surfaces. And thus black carbon has an adverse warming impact on Earth. Okay. Now if you see the cooling impacts, sulfur dioxide present in SOx emissions produces droplets of sulfurous and sulfuric acid in the atmosphere, which creates the haze of acid rain, correct? And that haze means that sunlight cannot reach the Earth's atmosphere, Earth's surface as effectively. You will see the atmosphere becoming foggier, so more of the sunlight is getting reflected back instead of getting absorbed by the surface. So that acid rain caused haze is causing a large cooling effect of minus 0.5 degrees centigrade. Okay. And nitrogen oxides are also a contributor to this acid rain. Organic carbon is also a contributor to this acid rain. So these are the cooling impacts. whereas these are the heating impacts. So strangely, many of the pollutants, while being extremely harmful to human health, has had a cooling effect which has partially mitigated the heating effect of global warming, which of course raises an important point. As our pollutant levels decreases by improving our emission norms, improving the pollution remedial initiatives, so we are emitting less SOx, less NOx in the atmosphere, these cooling effects are likely to go away in the next 10-20 years as we have more stringent emission norms. Okay, then this entire warming due to greenhouse gases is going to come into the picture. So there is a prediction that because of the cleaning of our energy technology sector, there is a possibility that if we just clean our technologies instead of doing CO2 mitigation, global warming is actually going to rise rather than decrease. Okay, even though that will also help us decrease our mortality due to pollution, which is certainly good, there is a risk side to it also that needs to be properly managed. Okay, and this one is the figure which shows the temperature rise over the last from 1850 to 2020 onwards, the observed temperature rise that has been observed from various types of observation systems. And we see that it starts from 0, which is the normal between 1850 to 1900, and is now going to around 1.2, 1.3, etc. And this is a simulated value, and this is due to natural variability only, what would have been expected, which is near 0. So all of this is due to human actions alone, as we have discussed. This figure kind of shows the relative impact of the various greenhouse gases that we have been discussing. So CO2 has an almost infinite stability in the atmosphere. So CO2, when it's there, even though it is absorbed by green plants and then respirated back, there is a natural CO2 cycle. But overall, if you add extra CO2, that CO2 will not go back down in any time soon. Okay, so it has relatively long half-life, and hence it will remain in the atmosphere for long periods of time. And we say that CO2 is the standard in terms of its global warming potential. So we are comparing all other gases' ability to heat up the atmosphere relative to CO2. So the global warming potential of CO2 in 20 years and 100 years is both 1. Methane is less stable in the atmosphere because methane is CH4 and we have free oxygen in the atmosphere. So slowly the methane oxidizes to form CO2 in the atmosphere. So if you put 1 kg of methane today, in a year, in 12 years, we expect half of that is half kg of methane would have been degraded to CO2 and only 0.5 kg of methane would have been left. So the half-life of methane is 12 years. However, it is a much more potent greenhouse gas compared to carbon dioxide. So it's 84 times as effective in heating the earth as carbon dioxide is over a 20-year period. And because of this half-life decrease, over a 100-year period is somewhat lower, 28 times more effective. Okay. Then you have nitrous oxide, which is more stable in the atmosphere. Its half-life is 121 years, which is even more potent, 264 times more powerful than CO2 in its heat trapping ability. Okay. And you have the other trace gases from refrigeration systems, which have much higher global warming potential. So these also are a significant cause of concern, even though they are emitted at a lower values by our today's energy infrastructure. So we can also measure how much this emission of CO2, nitrous oxide and methane has led to a rise in the concentration of these gases in the atmosphere. So here the value is parts per million. So parts per million means 10 to the power minus 6 in terms of mole fractions. So in 1960, the atmospheric CO2 level was around 315 parts per million, or 315 to the power minus 6 in terms of mole fractions. Due to the emissions till now, by 2020, this has increased to around 410 parts per million of CO2 emission, CO2 concentration in the atmosphere. So we can observe that the CO2 concentration is rising due to human activity. Similarly, we see that for methane's case and N2O case as well. For the methane case, we see that so methane is present in much lower concentrations. So here the values are in parts per billion. So 10 to the power minus 9. Okay. So this started at around 1500 parts per million and is today 1866 parts per billion. And N2O, nitrous oxide, is also present in very trace quantities from 300 parts per billion to 332 parts per billion. Okay. Now you might be wondering why, if these gases are present in such low quantities, are they effective? They are effective because since these gases were present in low quantities, they were not very effective in trapping the heat. But as their concentration rises, their heat trapping ability also increases, precisely because you don't have a lot of it. So you can think of it like if you put a drop of ink in water, the water becomes colored, right? The amount of ink is much low, right, compared to the total mass of water, correct? And if you put another drop, it becomes opaque to light. The situation is very similar here. A small amount of CO2 has a large impact in the transparency of atmosphere to infrared radiation, because after all, infrared radiation is like electromagnetic radiation, and what it is doing is making the atmosphere opaque to that radiation so that it reflects it back rather than transmitting it. Okay, just as ink does it for visible light. And so the small increase is sufficient to move the atmosphere from being transparent to being opaque, which is the cause for concern. So the IPCC has also projected what is the impact under various cases. Okay, so we will discuss this through several slides here. So let's look at this slide in detail. So this is 2020. This plot is up to 2017. So this is the historical CO2 emissions, CO2 concentration in the atmosphere. So it ended at 2017. So it's 400 ppm. And these are the possible projected CO2 concentration futures for different types of energy pathways that we adopt. Okay. So some are called low emission pathways, the light blue and the dark blue. Here the CO2 concentration is peaking by 2040 or 2050 to below 500 ppm and is then slowly declining. Then you have two types of medium emission pathways. Here the CO2 concentration is peaking in 2060 to 600 ppm, 550 ppm approximately, and then begins to decline. Another medium emission pathway is this yellow one, where the CO2 concentration does not decline but stabilizes by 2100 to around 600 ppm. And these are the high emission pathways where the CO2 concentration continues to rise at certain different rates to around 850 ppm and around 1100 ppm for two different cases. Okay. So we will see for these various cases what is the expected global temperature rise in the next few slides. Remember, today's CO2 concentration of 410 ppm has led to around 1.3 degrees temperature rise. Okay. So we will see how that has an impact. But before going into that, what is the current impact in the world due to this global temperature rise? And what are the spatial variations of these trends in different parts of the globe? So this figure kind of shows this impact. So it looks in 4 decades, 1980 to 2020, 4 decades, and looks at the decadal temperature rise in a certain region of the world over these 4 decades, and what is the trend in that temperature rise. And the color is going from 0.6 degrees centigrade per decade increase in temperature to minus 0.6 degrees centigrade decrease in temperature. Okay. And you see here the main trend is that the high latitude regions like the Arctic region, northern Russia, northern Canada, Greenland have seen much faster decadal temperature rise than other places of the world. That is, Arctic has been warming faster than other places of the world, much faster. Similarly, you will see that certain areas like Central Europe, then Central Mongolia, and also certain parts of land masses like Northern Africa, Central Brazil, Mexican regions have shown larger temperature rise than other parts of the world. So these regions, especially the land masses, have shown larger increase in temperature. Compared to that, the equatorial regions have seen lower change in temperature, and the oceanic regions have also seen lower change in temperature, with certain areas showing cooling impacts even. Okay, because of the various climatological and weather factors, the warming is not uniform throughout the world. Certain regions, the Arctic, certain landmass regions have warmed faster, whereas certain parts of oceans have even cooled because of this. Okay. So the warming is not uniform. There is significant heterogeneity, and that has significant impact on the climate as well. Along with this comes a change in precipitation levels as well. So these are decadal changes in precipitation levels throughout the world, again between these 4 decades, 1980 to 2019. And here the trend is in millimeters of rainfall received per year, how much it has changed. So from plus 200 millimeter per year to minus 200 millimeter of rainfall per year. So the more brown is, the drier those regions have gotten. The more blue is, the wetter those regions have gotten. And you can see here, China has become much drier, whereas India has become much wetter. Okay, so you can see there is a lot of local changes because of this global warming impact, and that is the difference between global warming and climate change. Climate change is the local impact in the climate due to the global change in the global temperature due to CO2 and other greenhouse gases. That's why we have these two terms. Okay. Certain parts of Australia have gone wetter, other parts have gone drier. The Central African regions and the Sub-Saharan regions have gotten actually drier, with significant droughts in these regions, whereas Southern Africa and parts of Northern Africa, Spain and Mediterranean have gotten wetter. Whereas much of the central mass of Europe and Western Russia have gotten drier with significant droughts. This has also happened in Southern Brazil and Argentina and in the Western US. Whereas Eastern US have received greater flooding. So because of global warming, certain regions, India, parts of Southeast Asia, parts of Amazon, Spain, Italy, etc. have seen extremely wet climate, more rainfall, more floods, whereas other parts like China, Central Africa, Eastern Europe, Western US have seen more droughts. Okay. So there are significant differences in how the precipitation has been impacted. So we have seen the CO2 ppm levels for the various scenarios, and here we will see the what those scenarios mean in terms of CO2 emissions and the mean surface temperature changes. So here is the CO2 emissions in billion tons of CO2 per year, and we are somewhere around 40 billion tons of CO2 emitted per year right now. Now in the very high emission scenario, we go in business as usual. We keep burning coal, keep burning natural gas, keep burning diesel, petrol as we are doing till the very end, around 2090 or something. And then the CO2 emissions continues to rise and track our increasing energy use goes to 120 billion tons of CO2 per year. Okay, and the CO2 gets doubled and you have the very high scenario of 800 or 1100 ppm of CO2. Okay, the high scenario, and what is the case in this case? So in this case, the expected temperature rise is going to be 4.5 degrees. Okay, the median, with you can hit 5 degrees also you are high ending. Currently it's around 1.1, 1.2, so you will get 3.5 to 4 degree temperature rise from 2020 to 2100, which is going to be catastrophic to the world. Okay. In the high emission scenario, what we are doing is we are focusing on energy efficiency, so the CO2 emissions are reduced, but not sufficient enough, so the CO2 is continuing to rise. Okay, the CO2 emissions per year are continuing to rise, though at a slower rate. Okay, so these are high emission scenarios where the emissions by the end of 2100 is still going to increase to around 80 billion tons of CO2 per year. And in these high emission scenarios, the expected temperature rise is going to hit 4 degrees centigrade. So a 4 degree rise in temperature from 3 degree rise in temperature from today's condition. Okay. Then comes the medium and the low emission scenarios. In the medium emission scenarios, the CO2 emission rise is going to peak at around 2040, 2050, and then is going to slowly decrease. So the CO2 emissions per year is going to slowly decrease but never reach zero till 2100. So 2100 we are expecting in this medium case around 20 billion tons of CO2 will be still getting emitted. Okay, so we are investing in renewable energy technologies or sustainable energy technologies, but still there is enough fossil fuel being burned that CO2 is getting emitted. So for this medium level scenarios, we expect the temperature rise to be finally to be around 2.8 degrees centigrade. Okay, still above the safe levels. So the Paris target is around 2 degrees warming. So current is 1.2. Based on the scientists' figures, 2 degrees warming, the damage can be reasonably managed without looking at extreme interventions. So still above that. Okay, and it will go above that by 2050 only. Okay, so it's not very far away when you think about it. And then there are the low and the very low emission scenarios where we aggressively look into the CO2 mitigation technologies today and start decreasing the emissions very quickly and hit net zero emissions either by 2060 or by 2080. So there is a net zero global emission target that when a country or the world together will not emit any CO2 based on its industries. Okay, and then it is followed by CO2 drawdown, technologies that are actually absorbing CO2 from the atmosphere. Okay, this can happen through reforestation effects. This can happen through carbon capture directly from air carbon capture. So those kinds of technologies that will be deployed more and more by 2060 or 2080 onwards. So only for these scenarios will our temperature rise stay within our 2 degree centigrade Paris climate agreements. Okay. So I will stop here for today. In the next class, we will look into further details on some of the impacts of global warming that is happening today. We have seen precipitation effects, temperature effects. We will look into it in more detail and also see how the future will change based on these predictions. And after that, we will start our introduction to renewable energy technology. So thank you for listening. Hope the class was enjoyable and clear. See you in the next class. Thank you.